continue, how would your system handle the case where a particular keyword appears in billions of posts? Would your current inverted index design need any modifications to maintain performance in this scenario? So the situation which we're talking about here is that we have keywords like we have words like and or those very popular words which don't have any particular meaning, but they are very popular here. So and they're not that useful even. So we need to do something about it, and well, the main thing we can do about it is to essentially filter words like and or etc. Because well, they don't give much meaning, but there are other words which will be very popular, like maybe football or something like that, and they may have billions of posts associated with them. And in this case, we also don't want to keep that inverted index that's in memory. We're using Redis sorted set, for example, for this. So we don't want to store it, in the memory, like billions of them. So even for other regular useful keywords, we still want to have some sort of limit. Yeah, maybe 1,000 posts associated with each keyword. That will be max. So let's say limit posts associated. With keywords to G1000. That will be pretty good. In certain situations we would like to have access to maybe more than 1,000 posts. So, but those will be very specific situations, and probably in that case we should just have some sort of cold storage from which we will be retrieving those indexes for more than 1,000 posts. Yes, we can have some sort of not in memory storage, could be some cold storage, let's say. Let's say for more than 1,000. And usually in that kind of situations, if user needs to really have access to more than 1,000 things, usually those type of users will be okay with waiting a little bit more. Okay, you correctly identified that common words like and or should be filtered out as stop words since they don't add meaningful search value. You propose a practical solution of limiting the number of posts 1,000 associated with each keyword in the in-memory inverted index, which addresses the memory constraints while maintaining good performance for most queries. You suggest using code storage for retrieving additional posts by beyond the limit when necessary, acknowledging that users would accept longer wait times for these less common extended searches. Minor suggestions. Consider adding a pagination mechanic that could work with your cold storage approach, allowing users to incrementally load more results beyond 1,000 limit while maintaining reasonable response times. For example, you could implement a token-based pagination system where the initial query returns the first 1000 results from your in-memory index along with a pagination token. When a user requests more results, the token could be used to query your cold storage for the next batch, perhaps retrieving them in chunks of 100 to 500 posts at a time. This approach balances performance with completeness by providing immediate results for common queries while still supporting exhaustive searches when needed. In an interview demonstrating this kind of thoughtful pagination strategy shows you understand both the technical constraints and user experience considerations. Yeah, we can have some sort of pagination. Yeah, it makes sense. The sample answer. There's a follow-up question that was based on your previous answer. Okay. Next question. How will the system handle queries with multiple keywords like tail and Swift? Yeah, so we can have like one option is to essentially is to do like intersection. So we take all the posts associated with Taylor, all the posts associated with Swift, and we're finding intersections. So we're looking for those which are in both. That's kind of one thing, and another way is to create like things like biograms. I think it's called grams. So essentially, we would have as a keyword, we would have Taylor, maybe Swift, we would have that kind of the keyword, the keyword with multiple words under one key, and then we also need to remember about all the combinations. So we need to have Taylor Swift, Taylor, and so on. So yeah, that's kind of another way, more efficient, because intersection for the intersection we would need to look through. We need to essentially filter out and get only those which are in common. So that involves iteration over possibly thousands of posts. Even if we're trying to have a limit to 1000, so that may also increase in inaccuracies. The final result may not be as accurate. But in that way we're saving space, generating all those diagrams. It's just or shingles. That's something which just like takes. It's going to take lots of space in our memory and may not be that useful. Okay, you provided two solid approaches to handling multi-keyword queries: intersection method and diagram approach, demonstrating a good understanding of search system design trade-offs. You correctly identify the performance implications of the intersection approach for queries with many matching posts, showing awareness of scalability concerns. Your explanation of diagrams and shingles as a potential optimization strategy was accurate, and you acknowledge the space-time trade-offs this approach introduces. Consider elaborating on specific performance metrics or thresholds that would guide when to use intersection versus diagrams. Okay, yeah. Would like to use diagrams if we need to be faster. For example, you may specify that intersection works well when keywords have fewer than 10,000 matching documents, while diagrams become more efficient when common word combination appear in more than 100,000 posts. During an interview, quantifying these trade-offs demonstrates analytical thinking and shows you consider real-world performance implications rather than just theoretical approaches. Discussing specific metrics also demonstrates your experience with production systems where these decisions impact the user experience. It will be helpful to quantify the performance implications of the intersection approach, especially for high frequency keywords that may appear in millions of posts. Um, mm, yeah, for example, tail up using 1 million posts and split up using 500,000 posts. The intersection operation will require processing all these entries, potentially causing significant latency. So I decided before that I wanted to sort of limit the amount, but yeah, that still might be a problem if we didn't have that limit, because limits also create other problems. In an interview, providing concrete numbers demonstrates your understanding of system bottlenecks and shows you've thought through real-world scenarios. You could also mention specific optimization techniques like Bloom filters or early termination strategies to show depth of knowledge about handling large-scale intersection efficient. Mm, mm, Ingestion. To handle queries with multiple words, we will create diagrams like Taylor Swift to store in our search indexes. Instead of indexing only singular words, we'll also index the diagrams. The diagram index is found. That would be preferred. Otherwise, the search service will need to take the intersection of the two individual words. Okay. Let me see what's the difference between shingles versus diagrams. So shingles are essentially they have more than more than two keywords. So that could be like for sentences we could use shingling. Um, yeah, but I need to learn more about that concept. Okay, how can we ensure such as queries are still fast in the case of many results like Taylor Swift? Um, yeah, so well, essentially we would have inverting indexes with diagrams or those shingles um, for more keywords, and that's optimization. Intersection uh, if we are careful and we keep that limit to 10,000 posts per keyword, for that kind of situation, intersection may be okay, but for bigger, if we're not allowed, if we for some reason need to keep more keywords associated, more posts associated with each keyword, we're not allowed to have smaller limits, then uh, uh, then intersection may not be as performant, may take just too much time. You correctly identify the need for inverted indexes with sorted sets to handle search queries efficiently. Um, your approach of using background strings for market keyword matching is appropriate. You correct potential performance issues of large result sets and propose limiting posts associated with keywords. Your solution doesn't fully address how to handle performance challenges when queries match millions of posts beyond simply limiting the number of top posts per keyword. A more comprehensive approach would include multi-layer caching, both a local cache with the search service and distributed cache. Uh, Cache shared across services. This would significantly improve performance or for particular queries like Taylor Swift by avoiding repeated processing of the same search terms. Multi-layer caching. Okay, for high volume queries like Taylor Swift, implementing a multi-layer caching will store both the search results and intermediate processing steps. The local cache will handle repeated queries from the same. But that's something which okay. Yes, that's when we have lots of searches. That's where we optimize. Uh, that's another option to cache it, and then we don't need to uh, we don't need to, let's say, update that index too often, or even, we don't need to even access it. Why the distributed cache would benefit all instances by storing popular query results. This approach is particularly important to discuss in interviews because it demonstrates your understanding of real-world performance optimization beyond basics indexing strategies, showing you can anticipate and solve problems at scale. Consider explaining more clearly how the sorted sets in your inverted index would be leveraged to efficiently handle high volume queries. Um, For popular search terms like Taylor Swift, sorted sets allow you to efficiently retrieve the top end results without scanning the entire dataset. You should explain how these sorted sets maintain posts in order by recency or like count, enabling log and retrieval operations rather than full scans. In an interview demonstrating this knowledge shows you understand both the data structures, capabilities, and how to apply it to solve real performance challenges at scale. Include a specific pagination strategy for dealing with large result sets to ensure consistent performance regardless of page number. Okay. When dealing with large result sets, implementing cursor based pagination using the last item's ID or timestamp is more efficient than offset based pagination, which degrades of larger offsets. This approach maintains consistent performance regardless of which page the user requests, as the database only needs to find records after a specific cursor value. In an interview demonstrating this knowledge shows you understand real performance consideration beyond basic functionality. Okay, elaborate on how you might implement caching for popular search queries to reduce database load and improve response times. For popular search terms like Taylor Swift, you could implement a query cache that stores the results of these frequent searches, refreshing them periodically rather than computing them on every request. This cache could be implemented using Redis or memcached with TTL set based on query popularity and data volatility. In interview demonstrating this knowledge shows you understand real-world performance optimization beyond just theoretical database design. For popular search terms like Taylor Swift, we could implement query cache that stores the results of these frequent searches, refreshing them periodically. Mm, periodically, rather than computing. Yeah, we can even use like CDN for that. Okay, since we're storing our posts already in sorted sets in our indexes, we don't have to worry about there being millions of matches. We only care about the first 10. To speed things up, we'll cache some search queries on a CDN so that the users get very low response times by retrieving results from the edge nodes very close to them geographically. For popular queries, we can use LRU eviction strategy to ensure our CDN contains only the most popular search queries. Okay, yeah, that's you can put like a CDNs, or you can have like also caches for those for those indexes. How can we make ingestion scalable and fast with millions of posts and billions of likes? Yeah, that's a good question. Yeah, that I sort of answered it. Yeah, so I used SQS, but so we would have, but maybe more scalable would be to more scalable would be to well, just having like a just having like by using maybe Kafka, that would be more efficient. We could have instead of SQS, we would have Kafka, yep, and for the Kafka we're gonna need some sort of small server which writes it to the Kafka writer, and yeah, that will allow us to sort of like slow down those events, and also make it's gonna make them retriable, so it will be much less likely to lose them, which is like another option. And then yeah, Kafka is very scalable. It can handle like millions of events per second, and then we're gonna have some sort of let's call it ingestion service, which is gonna process those things from Kafka and construct our inverted index based on that. Yeah, so that's for posts, and for likes it's actually very similar. So well, as I mentioned before, for likes we can have in our like service we can keep calculating those likes in memory, and then we don't want to make one billions of updates for likes. We don't want to update inverted index every single time the like happens, so we can limit that by having some sort of threshold. So for example, if we if the amount of likes uh, is more than so for example, those thresholds could be powers of 2. So if we go over the threshold, then we can write into our inverted index, and in that way we avoiding making millions of writes into inverted index. Your design effectively addresses the scalability challenge by implementing Kafka as a message broker to handle high throughput of posts and likes. You proposed an excellent optimization for like updates by using power of two thresholds to reduce the frequency of index updates, which is critical for handling billions of likes. Your approach with ingestion service to process events from Kafka and construct the inverted index shows good understanding of asynchronous processing for high volume data. Okay. Yeah, consider explaining how you would partition data in Kafka to maximize throughput for different types of events, posts versus likes. Yeah, we can have partition uh, well based on well we can have different Kafkas, yeah, for likes and different Kafka of posts. For high throughput systems, you could use Kafka topics by event type, separate topics for posts and likes, and further partitions the likes topic by post ID, or yeah, we can do it by post ID or user ID to enable parallel processing. This partitioning strategy allows you to scale consumers independently based on traffic patterns. For example, having more consumers for the likes topic during viral content spikes. In an interview demonstrating this knowledge shows you understand not just basic event streaming, but also how to optimize it for specific workload characteristics. Um, you could elaborate on how the ingestion service would be horizontally scaled to handle varying loads throughout the day. The ingestion service could be deployed as a cluster of stateless workers that can scale up and down based on the Kafka consumer lag or CPU utilization metrics. You may implement auto-scaling groups that add more ingestion service instances during peak hours, e.g. Evenings or weekends, and scale down during off hours. Additionally, you could discuss partitioning strategies in Kafka to ensure that processing can be effectively parallelized across your ingestion service instances. Adding details about failure handling and data consistency guarantees during ingestion would strengthen the design. Yeah, so with Kafka we can essentially have offsets which will allow us to reprocess things again and again, so we're not gonna lose those events. When processing millions of events, you could discuss how your system handles scenarios like network partitions, service failures, or Kafka consumer crashes. Consider explaining exactly how you would ensure at least once and exactly one processing semantics. And how you would handle data consistency between your cache and persistent storage during failures. Interviewers are looking for evidence that you understand distributed systems challenges beyond happy path, especially at scale where failures become inevitable rather than exceptional. Okay, sample answer. Um, Okay, so to limit the number of writes, we need to make 2-hour search indexes for the like. We need to make 2-hour search indexes for the like events. We can limit calling the ingestion service to only powers of 2. Our search indexes will have approximately correct ordering for posts in our search service when we retrieve the list of posts that match a given search query will grab more than we expect to return, e.g. 40 when we need 20. Then look up the actual counts for this post from the like cache, will resort and that final list before returning. Yeah, so we can improve that accuracy um, by making call to like cache. Yeah? So in that way we gonna get improve that results to be very accurate, and at the same time we avoid making lots of calls or lots of writes to our inverted index. It's a smart strategy. Okay, how would your system handle a scenario where then Kafka cluster experiences a partial outage or network partition? What impact would this have on post-search results, and what recovery mechanism would you implement? Yeah, so if Kafka cluster experiences a partial outage or network partition, so well, one problem is if Kafka is not available, then our writer is not gonna have things to write to, so we may lose sort of data. To avoid that part, then we can implement some sort of reconciliation mechanism. So then after that outage, we can essentially iterate through them, go through that database and search for things which were not ingested. Yeah, we can um, well, for post it's kind of easy. Yeah, we can we can sort of check which posts uh, were processed and which were not processed. Um, so that's kind of on one side. If Kafka is not available from the ingestion service side, then we can just retry from that last processed section. In Kafka we have offsets, so and that kind of will allow us to retry. So that's another strategy. And for like service, for like service here we don't actually use Kafka. Yeah, so that's kind of what comes to my mind. Yeah, that kind of depends what sort of side of Kafka is not working. Is it the things which happen after Kafka, or event writer is not able to find Kafka? Okay, you correctly identified the need for a reconciliation mechanism to recover data that couldn't be written to Kafka during an outage, showing awareness of data loss risk in distributed systems. You demonstrated understanding of Kafka's offset-based processing model, which would allow your ingestion service to resume processing from the last successful offset after recovery. You thoughtfully distinguish between different failure scenarios, writer side or consumer side. Kafka issues recognize that recovery strategies depend on which part of the system is affected. What needs to be improved? Your answer didn't address the impact on search results during the outage, which was explicitly asking the question users would likely see stale or incomplete results until recovery completes. During a Kafka outage, a new post or like counts updates wouldn't be indexed, meaning users searching would see outdated information. For example, a trending topic may not show recent posts, or popularity-based sorting could be inaccurate because the like counts wouldn't be updated. That's understandable. considering details about how would you implement the reconciliation process, such as using database transaction logs or timestamp to identify unprocessed posts, and how would you prioritize backfilling critical data first to minimize user impact. For example, you could implement a reconciliation service that periodically compares database timestamp with the last processed event timestamps in your search index, identifying gaps where posts were created but not indexed. This service could maintain a priority queue based on post popularity and age, ensuring high value content is recovered first during backfill operations, adding specific details about error detection mechanisms like health checks or heartbeats, and recovery produces demonstrates depth of understanding and about distributed system resilience that interviewers look for is your candidates. Okay, yeah, that makes sense. Yeah, we can sort of compare database timestamp and in our inverted index we can keep track of the last processed event timestamps. Okay, and how can we optimize the storage requirements of the system? Yeah, that's another good question. Yeah, so in this system, let's say we're gonna have 1 billion posts every day. We're gonna have we have 365 days, and we have let's say 10, for 10 years, and each post is, let's say, 1 kilobyte. That's gonna give us 365 let's say we have 1 billion posts per day, 306 365 billion. There will be additional zero here, so that will be like kilobytes, megabytes, gigabytes, terabytes, and then I think it's petabytes, so it will be a 6.5 petabyte of storage needed for 10 years, which is huge. That's why we can that's why it will be actually necessary to have something like cold storage, for posts, for those maybe older posts. We can search we can keep log of like which posts are accessed, which are not, and those which are not accessed recently we can just throw into cold storage. We still want to have them retrievable, but for those less access, it would be okay for user to wait a little bit more and just have access for them from the cold storage. Okay, based on post volume, retention period, and post size resolution, consider explaining specific criteria for which the post could be moved. Posts not accessed for X days, posts with fewer than views. Yeah, that's one idea. Add details on how system would track your access patterns, and identify candidates for cold storage access counters, time-based key functions. Elaborate on retrieval process when user searches for content in cold storage, including potential latency trade-offs and how to communicate this with users. Yeah, so they also use like a cold search indexes. But yeah, that'll be it. Yeah, thank you for listening.